Science in the Arab states. And I would like to welcome you to the session number 12 on groundwater governance. Of course, all the topics that we are going to hear today are related in one way or another to groundwater governance. One of the most important and the very early tenet of establishing groundwater government is setting the stage and establishing the basis for governance. And that requires a lot of data, requires information, requires management tools, which are things we are going to be hearing about today. I would like first to welcome our first speaker, Professor Jamal Sharaf. Professor Jamal Sharaf is a physicist. He is a professor of physics, radiation, and medical physics at the University of Jordan, Amman. He was also the Director General of Jordan's Nuclear Regulatory Commission. Professor Sharaf had a PhD from the University of Surrey at the United Kingdom in medical and radiation physics in 1994. He also obtained his master's from the same university in 1990. In addition to that, he also obtained a Master of Science in Nuclear Instrumentation from the University of Edinburgh at the United Kingdom in 1982. Professor Sharaf will talk about radiological analysis of groundwater. So I would like to ask him to kindly, please.
Good morning. I think I need to load. First of all, I'd like to define our objective from this presentation, that I will talk about the activity concentration in the groundwater. Then we will talk about dosimetry concepts. As we will see that radiation sources emit different types of radiation, as we are going to talk about. And these radiation are usually an energy. And when we absorb energy, the energy is enough to ionize our body cells. So we'll talk about this dangerous situation. Radiation sources are usually two types, either naturally occurring or man-made. Both sources emit one of or more than one type of radiation. Alpha particles, as you know, it's a positive nucleus of helium. Beta particle is negative electron, and gamma rays is an electromagnetic radiation. Let us first, before talking about the radioactivity concentration in water, let's just introduce some concepts about the radiation dosimetry. Measurements of ionization and energy absorption are the basis for radiation dosimetry. There are different definitions for dose. First of all, the absorbed dose, which is the energy absorbed per unit mass, which has a unit of joule per kilogram, or it's just called gray. But this absorbed dose doesn't tell us about what sort of radiation or what kind of radiation we have dealing with. So the equivalent dose was defined in order to allow or to differentiate between different types of radiation, and to tell us about the biological effect of radiation on the body. So it takes the quality factor multiplied by the absorbed dose just to differentiate between different radiation types, and its unit is sievert. Then, as different tissues of the body respond differently to radiation, we should take a sort of weighting factor for different organs of the body and multiply it by the equivalent dose in order to have the effective dose, E. So we have now the equivalent dose multiplied by the weighting factor of the tissue, and we take, as you see in the last equation, the summation, which means that maybe more than one tissue will be exposed. The last one is the committed effective dose. A measure of the total effective dose received over a lifetime, especially when we take the radioactivity inside the body, as in the case of water. We digest the water with radioactive materials within it. So most of the time, this radioactivity will stay inside your body, and you will continuously receive a dose. So they introduce the committed effective dose, which is the total effective dose received over a lifetime, tau, which is considered to be 70 years. These doses we are actually dealing with when we talk about water. And in the case of groundwater, we need to measure the activity concentration available in water in order to go back and calculate the received dose. The activity concentration measures by becquerel per liter. Becquerel means disintegration, how many disintegration it gives per second. I mean, when we have, for example, an alpha source within the water, how many alphas it emits per second. Each alpha, each one, is called becquerel. Becquerel per liter is the unit which we will use to define the activity within water. This value can be related to an effective dose per year, which means millisievert per year, using a dose coefficient. If we measure how many becquerel within water, for each radionuclide, there is a coefficient which tell us how many millisieverts within a becquerel. And the average annual consumption of water, how many liters of water we are using. The WHO guidance level for radionuclides in drinking water. The WHO gave a limit that it's allowed to have some sort of radiation within water, which is called an individual dose commitment, IDC, which was defined as 0.1 millisievert per year. And from this equation, we can see the guidance level of radionuclides in drinking water. Each radionuclide, each type, has its guidance level introduced by or given by the WHO. And they consider, or they calculated this guidance level, considering that we consume 2 liters of water daily, or 730 liters per year. The recommended reference dose level of the committed effective dose of 0.1 millisievert per year is also equal to 10% of the dose limit for measures of the population. The dose limit for populations is 1 millisievert per year. If you receive just 1 millisievert per year, you are safe. This is what they say. And they gave just 0.1 millisievert, which is 10% of that, to water. So it's very small or conservative limit given to the drinking water. If we see that the United Nations Scientific Committee on the effects of atomic radiation has estimated that the global average annual human exposure from natural sources is 2.4 millisievert. And just to remember, we are talking about 0.1 millisievert from water. So it's very small value, or very small percentage. And therefore, no harmful radiological health effects are expected from consumption of drinking water if the concentration of radionuclides are below the guidance level. Now, how we assess, or assessment of dissolved radionuclides in groundwater. The WHO again introduced the method how we estimate the dose within the water, the groundwater or drinking water, by first screening for gross alpha and gross beta activity to determine whether the activity concentrations are below levels at which no further action is required, or if these screening levels are exceeded, investigation of the concentration of individual radionuclides should be determined and compared with the guidance level. The outcome of this further evaluation may indicate that no action is required before a decision can be made on the need for measures to reduce the dose. A screening procedure is a practical approach which maximizes the reliability and the cost effectiveness of assessing the radionuclide content of water. The recommended screening level for gross alpha and gross beta activity are 100 and 8,000 millibecquerel per liter. If we have water with these levels, we consider it as safe. If the screening level is exceeded, then the specific radionuclides should be identified and their individual activity concentrations measured. According to these equations, if the summation of the concentration as compared with the guidance level is less than 1, we still in the safe side. If it's more than 1, This doesn't mean that the result imply that the water is unsuitable for consumption, because these calculations or these numbers were given for consumption for a complete year. If you are using the water for less than a year, the calculations will be will be different. Here are some standard method, international methods to measure the gross alpha and gross beta activity concentration, and they are very well known methods. And here are samples of analytical techniques used for radionuclide assessments if the screening exceeded the limit. Oh, sorry for some, I don't know why that happened. Some numbers are given in Arabic and the others are given in English, but never mind. I don't know, I sent all of them in English. Anyway, here are the main radionuclides that may be found in water: polonium, radium, thorium, and the three isotopes of uranium. This is very important numbers that ingested dose coefficient for adults, how many sievert per becquerel, is very small. As you see, it's 10 to minus 8 something for uranium, different isotopes of uranium. While for polonium, it's 10 to minus 6, which is 100 times higher than that. So, activity per radionuclide millibecquerel per liter equivalent to 0.1 millisievert. How much we need to take from each radionuclide to have 0.1 millisievert dose limit. So we need, the first number is 117 for polonium, while if we compare the last number, which is 3,000 for uranium, which means that the dose coefficient for uranium is very low, which means that a high activity of uranium must be available in water in order to get a dose of 0.1 sievert, which that is very important result, which tells us that if uranium as a natural isotope is available in water, if it's only the uranium, so we can subtract from that from the gross alpha and gross beta. And if after subtraction the activity concentration is this less than the limit given by WHO, so we don't need to worry about the quality of water. 1 minute? Sorry. Let me just, he gave me just 1 minute. Let me just go to the last, okay. Just to talk 1 minute about health risk assessment. It tells us that man-made radionuclides that we can't control, because man-made radionuclides can come from a reactor or a nuclear reaction somewhere, while the most important is the naturally occurring radionuclide, especially for groundwater, as the groundwater is in direct contact with soil that contains uranium or other radionuclides. So we cannot control it. We don't know when it will mix with water or not. The most important here that we need to consider in case of water that the global average annual dose per person from all sources, not only natural, of radiation in the environment is approximately 3 millisievert per year. We are allowed to have 3 millisievert per year. As we said before, 80% of that, which means 2.4 millisievert, are due to naturally occurring sources of radiation.